structural dynamics or theory of vibration of the structure, which is currently we are talking about bridges a little bit more in deep. Whatever Yogendra Singh sir has already shown you in the previous lecture will be kind of supported by or added on by the details that we are going to discuss here. I hope I'm audible. Aman, am I audible, right?
Yes,
Yes, sir,
yes,
you are audible.
you are
Okay.
perfectly audible.
Okay. Now, with respect to the dynamics of structures, we know what is, when do we call a load a dynamic force is when the force varies with respect to time, right? What, as a design engineer, what we are more focused upon while designing a structure is to find out the peak forces or the peak displacement that occurs in a structure. So if we have the peak displacement, we can directly calculate what is the force generated in the structure and we can design it accordingly. But in case of dynamic forces, what is more important is to understand, first of all, what is the variation of the displacement when the dynamic force is acting on the structure, to find out the variations. As we said, there is a single degree of freedom system, there is multi-degree of freedom system. A structure is an amalgamation of masses and stiffness at various locations. So we need to understand the dynamic properties of the structure, right? So in this particular lecture, what I want to give you is a kind of overview of the structural dynamics that we learn, how that structural dynamics comes into picture when you design bridges, and how it will make you understand whatever hands-on exercise is being done in the evening with respect to what you select when you do response spectrum analysis, what do you get when you do time history analysis, what do you get when you do modal superposition method in good softwares which are used for bridge design and structural design. So to give you that overview, what we are kind of talking will be with respect to what is the dynamic response of the structure. So we know from the Newton's second law of motion that when a body is acted upon force, the time ratio of change of momentum equals that particular force. Now, in terms of structures, as Vaising sir has already told that yes, we can lump a mass. I mean, if it is a floor, if it is a pier, we can lump the mass that is coming from the superstructure on top of the pier. So that mass that comes as a part of the seismic mass can be taken as a constant, taken out. So we get the equation which is mass into acceleration, right? Which is the inertial force that we talk about. Then we use D'Alembert's principle for a system, like a simple system which is shown here is a mass spring model, which is put on a frictionless surface, and the spring is attached to a very rigid body. So if I draw the free body diagram, and this particular body is being subjected to a external force P of t, the force which is varying with respect to time, and we are trying to monitor the displacement time history of this particular body, right? So in order to solve it, yes, we are writing down the we are drawing the free body diagram, and by equating the using the D'Alembert's principle, we find out that the unbalanced forces is equal to the mass times the acceleration of the body. When we rearrange this is the classical equation of motion that we get, that is mu double dot plus ku is equal to p of t, which we call as the equation of motion. Now, when I consider damping in the system, the damping being modeled as a mass dashboard system, to make it understand, like in a structure, the damping which is inherently present. We are not talking about any viscous dampers externally provided in a structure. We are talking about the damping that is inherently present in the system, which comes into picture when there is cracks, micro cracks which are generated in concrete when there is a seismic action, or in a steel structure where the bolt slips and all. Damping is inherently present in the system. So to model that damping, we are representing that damping that is there through a viscous damper. We use the simple C as the damping coefficient, and the way we look at it is like, okay, it is mathematically easy for us to solve the equation of motion if we consider damping as an equivalent viscous damper that is present in the system. We cannot quantify the damping as such. Yes, we are quantifying the damping ratio through methods like logarithmic decrement method or half power band method, that is separate there. So we look at again the mass spring dashpot model, again on a frictionless surface, and being subjected to an external force P of t. Right, when it is subjected to a P of t, we are looking at the displacement history of the body. So when we write the equation of motion for this particular equation, we again get mu double dot plus the reactive force due to the damper is coming into picture, the reactive force due to the spring is coming into picture, that is equal to the external force that is applied. This is after rearranging, like D'Alembert's principle, we have to write the what we have done previously is like mass into acceleration will be the unbalanced force that is acting upon the system. This has been rearranged and put as an equation of motion that we normally know as, right? So when a body or when a structure is subjected to an earthquake force, what is happening is that there is an incoming earthquake that happens. The incoming earthquake is not an external force that we look at as a like a load kept on top of a slab, or wind load, or any kind of other load that is externally applied to the structure. The earthquake is like a ground motion that comes through the ground, which applies a certain acceleration, certain displacement on the ground, and due to the inertia of the building or the structure, the forces are generated in the structure, whether it is a pier or a building, it is generated, right? So we have a solid, a rigid ground body displacement that is happening here, then a relative displacement that happens in the members of the structures that is creating the reactive forces. So the force, reactive force due to the stiffness that is generated, or the forces generated due to the damping, cannot generate if it is a rigid body motion. There should be some relative motion that is generated. So in during a ground motion like inertia, we all know the example that our teacher says with respect to inertia. When the bus moves, we feel ourselves to be pushed back. So when the earthquake comes, let's say left to right, the structure moves from right to left, and that creates a kind of inertial force that is generated in them. And if we draw the free body diagram and write the equation of motion, we get the equation of motion mu double dot plus the reactive force due to the damper, the reactive forces due to the stiffness of the columns, the members that we consider, is equal to minus mu g double dot. So these theories you can find it in any classical theory of vibration book, and you can understand it easily. But what you need to understand is there is a certain kind of what do you say, simplification that we have done while analyzing this type of structure, right? In case of the previous structure, the mass spring dashpot model, we see that we are considering only one motion that we are looking at, that is a linear motion from left to right, right? In terms of left to right or right to left, this u is the only displacement parameter that we are interested in terms of a structure. If it is a 3D structure, you know, at a particular node in a 3D structure, there are 6 degrees of freedom, which corresponds to 3 translations and 3 rotations. If I consider, I mean, if I have a regular building, I can simplify it and say, okay, whatever, I can look at only the 2D format of that particular frame or a pier, and look at what is the response that the pier is giving. So I reduce my 6 degrees of freedoms to a 3 degree of freedom, wherein in a 2D model where you have only 2 translations and 1 rotation. Again, I can make an assumption and say that, okay, the axial deformations I can neglect, and I can say only the flexural deformations are going to occur. So I remove one of the axial deformation or the vertical translation that is there, I can remove. I can also say, okay, whether the mass has any rotational component attached to it, there is nothing related to such a thing. So I can reduce it to a single degree of freedom system, right? So this is the way we look at static condensation. The terminology that comes in a structural dynamics books with respect to static condensation is to make our life easier, calculation easier, by taking certain kind of assumptions with respect to the building deformations and the kind of way it responds, right? So degrees of freedoms, you understand, I've given the definition, like the number of independent coordinates required to define the motion or deformation of a structure is called the degree of freedom of the structure. So you might be dealing with a single degree of freedom system, you might be dealing with a multi degree of freedom system. The way you model as a design engineer, sir was saying with respect to a pier drawing he showed, with respect to a single degree of freedom, you can assume you can have multiple masses being lumped at different height of the pier, you can consider that also. So the kind of answer that you're looking for, the refinement of the answer that you're looking for, considering the complexity of the calculations, comes in play in terms of how you want to solve a problem. So before we proceed into multi-degree of freedom system, we want to look at simply about single degree of freedom system. Let us make our understanding better and then jump into multi-degree of freedom system. So, you know, a free vibration of a single degree of freedom system, why do we do? The free vibration of a single degree of freedom system is where we do not apply any external force to the single degree of freedom system. A mass, some damping value might be there, it may be damped or undamped, there will be a stiffness component there, and then we are applying an initial displacement or velocity to understand how the system performs, and what are the outcomes of those free vibration analysis is to understand the natural frequency of the single degree of freedom system. you know the natural frequency is expressed by square root of k by m, which means the natural frequency of the system is directly proportional to the stiffness of the system and is inversely proportional to the mass of the system. Which means what I want to say is, if my stiffness of the structure is very high, then the frequency will be also high. Conversely, when you look at time period formula, it is inversely proportional, which means if I have a very stiff structure, you need to make a, I mean, follow along with me, keep this in mind, so that it will be easy for you to understand what is going to happen next. So if you have a very stiff structure, your time period will be very low. If your stiffness is extremely low, that which means your time period will be very high, correct? And if you have a large mass on top of the structure, your time period is going to also increase. If you have low mass, I mean, it is the inverse of that particular thing, right? So these are certain terminologies that you know. Now, if you look at this particular experiment, this video, I hope, Aman, this video is visible, right?
Yes, sir, it is visible.
Okay. So what you see, all of you, what you see here is a uniaxial shake table, which is moving from left to right. The person who is doing the experiment is going to shake the table at an increasing frequency. And you see three masses kept on top of it. Three structural systems that is kept on top of it. It is easy to visualize that all the three masses are the same, but there is some difference in the stiffness of the system. The extreme left being a rigid structure and the extreme right being a very flexible structure. So think in your mind, be with me and think in your mind, what will be the frequency, which one will be excited first, which one will be excited second, which will be excited third. Keep that in mind, right? And see, when the first one is getting excited, whichever one it is, what is the behavior of the other two, right? Let's quietly see what happens. So he's slowly increasing the frequency of the motion of the table. You can see at 4 hertz, suddenly the extreme right one is getting vibrated in a little more agitated fashion. It is like a very high value. If you measure the deformation, it will be very high at 4 hertz. And then he's further increasing. Then you see the response being lowered, right? The displacement has reduced for the extreme right specimen. Now, when the frequency is getting increased, you see the rightmost extremely flexible kind of structure is not responding very vigorously, but the middle one is showing a higher response, higher than even the most flexible one. So at 6.35 hertz, the middle system, the intermediate system is showing highest response, which again starts reducing when the frequency is increased. And now is further increasing. You can listen to the sound. So you see that at 11.35 hertz, at 11.35 hertz, the extreme left, that's a rigid mode most जो system tha, that is vibrating very vigorously. But correspondingly, what is interesting to see that the flexible, most flexible system, which had vibrated very rapidly or vigorously at 4 hertz, was almost standing like it is not being disturbed by the shake table at all, right? So you understand certain traits that you have seen with the single degree of freedom system. right? So what do you do with respect to solution of, I mean, we need to know that if I have a single degree of freedom system and I kind of disturb it by giving an initial displacement or velocity, what will be the displacement time response of that particular single degree of freedom system? So how do I find out that answer? The easiest way is to use the classical way which we have learned in our mathematics in our 11th and 12th standard. That is by using the solution of second order linear differential equation, that is finding out the solution of the homogeneous equation, right? So how we can do that is by assuming, I mean, we know the response is like harmonic, we can assume a harmonic tentative solution for this particular equation by writing c1 sine omega t plus c2 cos omega t, omega being the natural frequency of the system. And then what you can do is by solving this particular equation by using the initial condition, that is maybe you have given it some initial displacement or initial velocity, you apply that particular condition into the system and then solve for the coefficient c1 and c2, and you come up with this particular solution of displacement time history that you see here, which consists of the initial displacement value cos omega t plus initial velocity by omega n sin omega n t. This is the solution of the displacement time history of the single degree of freedom system when it is undergoing free vibration, right? And as a design engineer, what we know want to know is the amplitude of this particular motion. We can find it out by doing the square root of the initial displacement square plus this particular second term, right? When we have a forced vibration, right now we were looking at free vibration when there was no external force but some initial displacement or velocity was being given, and we have a solution by solving the homogeneous solution. But if we have a forced vibration, which means you have an equation of mu double dot plus ku is equal to p of t, how do we solve it? We have a particular solution and we have a homogeneous solution, right? So we have to combine both of them and kind of find out the answer. If we have damping also present in the system, we know from our IS codes and all, what is a damping ratio that we consider for our steel or RCC structures that we have, which is like 5% that we assume. And we know for a fact that if we use the damping frequency, I mean, there will be a difference between the frequency for a damped structure, natural frequency for a damped structure and a undamped structure. But when we consider a damping ratio in the range of 0 to 20%, if we use this particular formula, we know that there is not much difference between the both. So that is why we see in the textbooks that, okay, people go with natural frequency itself even for a damped structure. And then damping ratio, as I earlier mentioned, this is the one that we are measuring experimentally through logarithmic decrement method or half power band method. And that is related to the damping coefficient that is used in our equation of motion, right? So when we have this forced vibration, um, being given to a single degree of freedom system. This is an undamped system, mu double dot plus ku is equal to p of t. We assume, let's say the problem is with respect to the structure subjected to a sinusoidal forced frequency due to a machine or anything. These are very simple problem. That is why we are able to use the classical form of solving the second order differential equation. So you have the homogeneous and the particular solution. For the homogeneous solution, we are assuming per certain form c1 sine omega by omega t plus c2 cos omega t. For the particular integral, we are assuming that this is the general form of the solution where omega bar represents the forcing frequency. Whatever that machine is going to run, what is the forcing frequency of that particular machine. So as a classical way of solving, we solve for the particular solution first. We club the, I mean, I'm just solving this equation for your, I mean, understanding. We a particular solution is given by g1 sine omega bar t plus g2 cos omega bar t. How do we solve it? We substitute this in the equation of motion above, mu double dot plus k is equal to pt. We get some form in sine omega bar t and some form in cos omega bar t. We club it and we take up a certain form which applies with the equation, and then we take it out and then apply it in the homogeneous equation and use the initial conditions of whatever the initial displacement or initial velocity is there. We solve it for finding out c1 and c2, right? And this is the final solution. You can open up AK Chopra or you can use any other method to find out what is the equation of motion. I mean, you can find out with respect to this, what is the displacement time history that we want to look at, right? This is the way it looks like. So there are two phases in this. There is a transient phase and a steady state. So an external machine is applying certain force on the system. As long as the machine will be on or the forcing function will be active, you will have the steady state going all along. The transient state is the one that may die out if you have damping present in the system, right? So you have the forcing frequency, which is this particular uh, uh, being applied to the structure, and when I look at the response of the particular structure, the total response will be this, but the steady state is like this itself. But if you have damping present in the system, what will happen is you have this particular total response and you have a steady state response if it is there. I mean, you are differentiating. The total response consists of the homogeneous solution and particular solution, but after a while the damping dies out the transient form of the vibration, and only the steady state remains, right? So till now whatever we have seen is what you start at the beginning of a theory of vibration class, wherein you look at a single degree of freedom system. You do the free vibration analysis to get the natural traits of the system, that is the natural frequency or the time period of the system, and then you use the then you have the forced vibration problem, where you have p0 sine omega bar t, or any step function or an impulse function, and you use the classical form of using the particular solution, homogeneous solution, to find out the displacement time history of the system, right? That is what we have covered till now. That is what I have summarized. Now, what is the use of such a kind of doing single degree of freedom system? Comes in the form of response spectrum analysis. So the next phase that I'm going to explain to you is what is a response spectrum method. How does a single, whatever we have learned, a single degree of freedom system appear, maybe a multi degree of freedom system? What is it, the use of understanding a single degree of freedom system? I'm going to explain through the method of response spectrum analysis. So what you see here, on the image here, is the accelerogram, where you can see the acceleration record of the El Centro ground motion. Now this is a record of the acceleration versus time of an earthquake, which is of a period of 30 seconds. You can see you have n number of data, as sir was saying that a recording station will record the horizontal components, the h1 and h2, and the vertical component of the ground motion. This is just one of the horizontal component of the earthquake El Centro ground motion recorded at a one particular station, right? So you can have, for a particular earthquake, you can have multiple recording stations recording the same earthquake, but having different values coming up. So this is one of the records, and you can see by integration you are looking at the velocity and the displacement of this particular accelerogram in that particular way. So if I use that same El Centro ground motion, the acceleration record that is there, and I apply it to my single degree of freedom system, let's say the same shake table, think of it as a big shake table wherein I have put 3 single degree of freedom system on top of it. What is the traits of these 3 single degree of freedom system is that the time period is varying for them. That is the natural time period of that single degree of freedom system. In one case it is 0.5 second, in the other it is of 1 second, and the third one it is of 2 seconds, similar to what we have seen in that video with respect to increasing time period from left to right. That is the way it has been given here. But what is the other trait that you see? That for all of them the damping ratio is the same. So we have a system where single degree of freedom system in which the damping ratio is same. They all three have been kept on top of the table, and somehow we are measuring the peak response of the system, right, when it is being subjected to a ground motion. So rather than applying an increasing amplitude of frequency to the shake table, we are applying the natural ground motion, the recorded El Centro ground motion, to the base of the shake table, and we are recording the displacement time history of, or deformation time history of the system, and we are finding out what is the peak value out of it, right? This 2.67 inch that you see here is the peak response of the single degree of freedom system when it is being subjected to a ground motion, and the system has the system is linear system, and it is having a constant damping ratio, right? So there are certain terms that are coming. We'll compile them at a, few slides later. So what you see here is, as the time period is increasing, which means you move from the left side of that table, which was a rigid structure, to a very flexible structure. So obviously you intend to see a larger deformation present in the system when it is subjected to that particular earthquake. Just for the academic purpose, if we go the opposite way around, now we have a system, a linear single degree of freedom system, having a constant time period of 2 seconds, which is that flexible system. But now the damping ratio is getting increased. So you have a system with zero damping, you have system with 2% damping ratio, and you have a system with 5% damping ratio. So you understand, right? If the damping increases in the system, it is going to reduce the deformation that or the response that is there, it is going to reduce, right? So that is exactly what you see, the deformation, the peak deformation response. The system with zero damping is 9.91 inch, Whereas the system with the 5% damping ratio, you see a reduction in the peak value of the displacement time history, which comes down to 5.37 inch. So you see two aspects. If the system becomes flexible, the deformation increases. If the damping ratio increases, the response decreases. I hope it is absolutely clear to you now. So what can we do with this peak response? As I said, as engineers, we are more interested in the most peak response, even if it is a static force or even if it is a dynamic force that is acting on the system. We are interested only in the peak value so that we can design the structure so that it can cater to that particular force that is coming into picture. So if I have the peak acceleration, I can find out the base shear, that is mass into acceleration. If I have the peak velocity, I can find out the strain energy. If I have the peak displacement, I can use it to design my non-structural components, as well as I can find out what is the maximum deformation, whether to do, I mean, what is the effect on the overall structural performance. So it has different uses in them, right? So the definition, I want you all to have an attention on the response spectrum definition that I have provided here. A plot of peak response. This is the first term that you need to have an peak response. I'm underlining that I'm looking at the time history, but when I'm plotting the response spectrum curve, I'm looking only at the peak response, whether it be displacement, pseudo velocity, or pseudo. We'll come to what is pseudo, what is non pseudo. We'll come to that, but we are looking at peak response of either displacement, velocity, or acceleration of a series of linear single degree of freedom oscillators. So it's a linear single degree of freedom system of varying time period. So we are increasing the time period. We are going from a very rigid system to a very flexible system, and for this, for a same damping ratio for a particular ground motion. So you remember, I have a big room, a big shake table, on top of which I have kept multiple single degree of freedom system, like the video that we have seen. We have, from the rigid structure to whichever is my period of interest, I can have a period of interest from 0 to 4 seconds. So I can have different single degree of freedom systems of 0, 0.1, 0.2 till 4 seconds. I can go. All those single degree of freedom systems should be linear, and then I have to ensure that they have the same damping ratio, and then I am subjecting that table to a ground motion, and then I'm looking or measuring, by any means I'm measuring the peak response, whether it is displacement, acceleration, or velocity. I'm measuring, and then what I'm doing, I've got the responses of these individual linear single degree of freedom system when it is subjected to this particular El Centro ground motion, and I'm measuring out all the peak responses from them, and then I'm plotting a graph wherein my y-axis is my displacement and my x-axis is my time period. It is not time in seconds, like your ground motion might be 30-second long, but here I'm talking about 0 to 4 second time period, natural time period of the single degree of freedom system that I have varied by using different single degree of freedom systems, right? So this corresponds to 2.67, corresponds to 0.5 second time period structure. uh, for a time period of 1 second, the peak response that I'm obtaining from my single degree of freedom system is 5.97, and the one that I'm obtaining from my time period of 2 seconds corresponds to 7.47, right? So if I plot the peak responses with this manner, that the x-axis represents the time period and the y-axis represents the displacement response, the peak displacement response of the system, this is what is known as a response spectra, the displacement response spectra. Now, I hope this is clear. Like peak response that we are measuring is the response spectra. We know a simple relation relating the displacement to the velocity, which is omega n into the displacement will give me the velocity. If I do omega n square, natural frequency square into displacement will give me the acceleration. Rather than finding out the from the displacement, if I differentiate it once, I'll get the velocity. If I differentiate it twice, I'll get the acceleration. Rather than doing that, I'm going this particular way of multiplying it with the natural frequency. Omega n into t gives me the velocity, and omega n square into t gives me the acceleration. This is a simplified way of finding out the velocity and acceleration. That is why the name pseudo velocity and pseudo acceleration comes. If I differentiate and find out in the direct way, I can call it as the velocity as well as the velocity spectra as well as the acceleration spectra. But since I'm using the relation omega n square into t and omega n into t, whatever response that I'm going to get in terms of velocity and acceleration, I have to call it as the pseudo velocity and pseudo acceleration. That is the only difference between the two. So this is displacement spectra of single degree of freedom system when it is subjected to el centro ground motion. This is the pseudo velocity spectra of the linear single degree of freedom system of varying time period but similar damping ratio when subjected to el centro ground motion. And this is the pseudo acceleration plot which shows the peak acceleration response of the linear single degree of freedom system when it is subjected to el centro ground motion. Right? Those nitty-gritties I might be missing in damping ratio in one, but the whole sentence reads: one linear single degree of freedom system subjected to el centro ground motion, a single ground motion, time period is varied, damping ratio is kept constant, and I'm looking at the peak response. So I get displacement, pseudo velocity, and pseudo acceleration. In our case of structural analysis, where we are looking at buildings and bridges, the damping ratio is almost less than 20%. So if you look at the textbook plots of real acceleration versus pseudo acceleration, real velocity versus pseudo velocity, in this particular range of time period that we are looking on, the damping ratio that we are looking at, there is not variation between the pseudo acceleration and the direct acceleration. So that is why in our line of work, we are happy to use pseudo accelerations and pseudo velocity, right? So what can be done? All these three are related to one another. You can see at the top of this particular slide, each of these are correlated. That is, the displacement spectra, the pseudo velocity spectra, and the pseudo acceleration spectra are all related to one another. So what can be done? They can be plotted in one particular graph itself as a tripartite graph, wherein your y-axis is your pseudo velocity, your x-axis is your natural time period of the structure which you're considering. It may be a bridge or a building, doesn't matter. And then you have an axis which goes like this, which represents the pseudo acceleration plot, and a graph which goes like this, which represents the displacement axis of the tripartite plot. So how to read this particular plot is, if you figure out the natural time period of your, let's say currently we don't mix it up, we say a single degree of freedom system. If you find out what is the natural period of the system, if it comes out to 2 seconds, you take this particular plot till you reach the spectra. I'm not calling it spectrum. It is a single ground motion that is plotted here. So this is a spectra. I drop a perpendicular to each of the axes. So if I drop a line perpendicular to the pseudo acceleration axis, I am reading pseudo acceleration of 0.19 g as the peak pseudo acceleration that I'm reading from the response spectra. If I drop a perpendicular to the velocity axis, the value that I'm reading is the peak pseudo velocity that this particular single degree of freedom system of natural time period 2 seconds is going to respond with. And this, when I drop it to the displacement axis, the peak displacement that is observed in the single degree of freedom system when it is subjected to el centro ground motion is 7.47 inches. I hope you all are able to now understand how to read the tripartite graph, right? Now, just before we go into the characteristics of the response spectrum curve or the tripartite graph, let's look at how can you plot the response spectrum curve. So you have response spectrum curve for a given ground motion can be developed by ground motion ordinates are defined at every 0.02 seconds, which means the accelerograph which measures the ground motion. You saw the el centro ground motion was a duration of 30 seconds, but the accelerograph which measures that particular acceleration reads that record. The data gets accumulated, let's say at an interval of 0.01 seconds, which means your 30-second ground motion right now has 3000 ordinates which are being measured by the accelerograph. So here, let's say 0.02 seconds we have that being measured. So now what after that, once we have the recorded data, then we select the time period, natural time period, and the damping ratio for the single degree of freedom system whose response we are interested in, right? And then we compute the deformation response of this particular u of t ground motion by any numerical methods, like what we earlier done for a single degree of freedom system where we use the classical methods of homogeneous and particular solution. It's easy to think when it is a harmonic load, pulse load, or any kind of impulse load, step loading, it's easy to think. But when you have 3000 data points and you have to solve that equation of motion, mu double dot plus cu dot plus ku is equal to a p of t or a minus mug double dot, that ug double dot consists of 3000 data points of acceleration that needs to be considered. So we have numerical methods available for them. We will come to that particular way how to solve it using time marching schemes. We'll come at the later when we look at time history analysis. But then once we have done that computation, we get the natural, what do you say, the displacement time history response of the structure, and from that we look at the peak value, peak displacement that is there, which is determined u0, peak value of the displacement time history. Once you have got the peak displacement, the peak velocity or the peak acceleration can be easily found out, and then you repeat it for different ranges of time period, and you can even find it out for the different damping ratios also you can find out. And I mean, that plot that you saw for might be for a damping ratio of 5% or 2%. You can vary the damping ratio based on the structure that you're considering. I mean, normally we consider steel structures to have lesser damping. Yes, the code has combined them currently, saying that the RCC and steel structures have the same damping ratio. But there are cases where steel structures will have damping ratio in the range of 2%, 1%. You can have tall buildings where the damping ratio is very less. So to consider all these cases based on the problem that you're solving, you have to choose the damping ratio and then repeat the process again and again. And then you can either produce a single spectra or a combined spectra uh, in terms of a tripartite graph or a single graph, whether whichever plot that you're interested in. If you're interested in finding base shear, you have to get the peak acceleration that is there. Acceleration spectra is enough. If you're looking at, let's say, a complete overview of what is a displacement or things coming like that, you might need a tripartite graph. Now, to understand the tripartite graph better, you can see the tripartite graph now has been given a certain definition, that is the acceleration sensitive region, the velocity sensitive region, and a displacement sensitive region. Why these names have come in, you need to understand this. This is the spectra, again the tripartite graph of the El Centro ground motion that we have considered. Now in this, if you see at a very, let's say time tn less than 0.035 seconds, think of it, time period is very low, which means what we are looking at right now is a very rigid structure, right? The time period is very, very low. If you have a rigid structure, what is happening? Which means when the ground is moving, when the acceleration or this ground is getting displaced, the rigid body or the rigid structure is also moving alongside with it. So whatever is the ground acceleration, the same will be the acceleration of the structure that is above. So that is why in the initial portion, even though this particular graph is showing a little bit a peak value, but you can understand that if I plot a line, let's say I start from here and I drop a line with respect to the acceleration graph, this line represents the peak ground acceleration ke corresponding, zero period peak ground acceleration ke corresponding, what is the value that comes. So you have a region, like if you have a short period where you expect the ground acceleration to be the same as the floor acceleration, that is the region where which is corresponding to the rigid body, where the time period is very low. The same goes for a flexible structure. When you have time period greater than 15 seconds, currently we are talking about 0.035 and 15 seconds. It is not kind of a rigid number that we are looking at. It can vary, but right now for our understanding, let's say the time period is greater than 15 seconds, which means it's a very flexible structure, right? In case of a flexible structure, what will happen? The mass will be on top and the ground will be moving like this, and the mass will be staying stationary. There will be related deformation in the columns or the beams or the piers that is there, which was not there in case of a rigid structure. In case of t is equal to 0.035, this is what is happening, if you can see my hand carefully. Whereas in case of a flexible structure, this is what is happening. So there is a related deformation. The mass stays still, but the structure is moving. So you have whatever is the ground displacement, that is the same as the displacement that the mass is undergoing or the system is undergoing. So you have very rigid and a very flexible. You see what is happening in the intermediate region. Let's pick out the acceleration sensitive region. Why we are calling it is because if I plot with respect to zero period, I plot a line perpendicular to the acceleration, you see what is the increment of the, there is some amplification in the acceleration data, which means for this particular time period, whatever may be the time period that I'm considering in this particular region, there is an amplification, the acceleration that I observe. If I look at this particular region, that is between 3 seconds to 10 seconds, which we are calling as a displacement sensitive. If I plot this thing here, here it is same as the ground displacement, but here there is an increment, there is an amplification of the ground displacement or the structural displacement that we see corresponding to the ground displacement. There is an amplification, right? The velocity sensitive region is where we have, again, this region is where the velocity is varying with respect to the ground velocity that is getting observed. So we have certain regions which are earmarked. So we have talked about less than 0.035, We have talked about greater than 15 seconds. We have talked about a region which is between 0.0535 to 5 seconds. But what researchers or analysts have seen that in the region of 0.035 or 0.125 to 5 seconds, the amplification in the acceleration in corresponding to the ground acceleration depends only upon the damping ratio. Whereas in this particular region, A to B, it depends upon time period as well as damping ratio. From here, the acceleration amplification depends only on the damping ratio. So you can see a straight line, a dotted line being plotted here. Amplification is there with respect to the ground deformation, but it doesn't change with respect to the time period. So I'm moving from a time period of 0.125 to 0.5, but then also the straight line more or less balances out, or gives me a constant value of peak acceleration that I'm finding from the system. Right? Understood? So that is the characteristics that the ground motion is showing in a certain time period, that it has a certain amplification, but it doesn't vary with respect to time period. It varies with respect to damping ratio. In certain region, it varies with the time period as well as damping ratio. So you can see here at this particular location, there is amplification in the acceleration value. If I move from left to right, there is an amplification that happens here, but in this location, it doesn't happen. If I bring in the damping ratio also into picture, this is for, let's say, if I for a second, if I consider that this is for 5% damping, this particular plot of curve. If I ask you what will be the response spectra for the same El Centro ground motion if I considered 0% damping, will it come above or below? Give a thought to it. If the damping ratio is 0%, where will be the response spectra curve occurring? Will it be above or below? And if I consider damping to be very large, I mean, think in the opposite way. We talked, if the damping ratio increases, the response of the structure decreases. So when I'm looking at even a dynamic system, the response is going to decrease. So if I have higher damping ratio, it will come below the curve, less than 5, I mean, 5% curve ke niche aayega. And if I'm considering a 0% damping ratio, the responses will be like, the spectra will be somewhere like this. Don't go with my, I mean, I have totally exaggerated, but it will be following like this if I have a 0% damping ratio that I'm considering, right? So after this discussion, you have to be very sure that okay, these time periods 0.035, 0.125 are very typical of this El Centro ground motion. But when people looked at multiple ground motion, you cannot design you the response spectrum. I cannot use a single ground motion. Even this is an El Centro ground motion. This has already occurred, right? There is nothing new in this. Can I use the same response spectra in a place like Roorkee? No. Is the ground motion that El Centro represents caused due to the same tectonic action? I need to explore. So for a particular particular structure, whether it's a bridge or a building, I need to consider multiple ground motions. And I also need to consider what those ground motion represents, what type of tectonic activity has caused that particular ground motion. If Roorkee is not a strike slip kind of a thing that happens in San Francisco, if a lot of data is available from California, can I use it in Roorkee? No, probably not. One it may be the soil condition may not be the same. The tectonic motion is, one is strike slip, here is a thrust fault. It cannot be the same. So you need to consider multiple ground motions should be considered. You will need to look at the traits of the response spectrum characteristics curve. You need to do a statistical analysis to find out what is a mean plus one standard deviation, etc. You need to consider, and then only you need to come up with the response spectrum curve that we have in our code, right? You remember the response spectrum curve that we have in our code with respect to doing equivalent static force method analysis as well as response spectrum analysis. It's a very smooth, right? If you look at this particular thing, it's very jagged kind of a thing. It is having peaks and valleys, etc. If you do use more earthquakes and plot an average kind of a mean curve of 10 or 11 response spectras, yes, it might smoothen out, but it needs further refinement to get the smoothest curve that we see from in our particular code. So how to plot? Are there any methods available to plot the response spectrum curve? Yes, there are methods available like this Newmark and Hall method, wherein they have given for different damping ratios, they have given certain amplification factors for the acceleration region, for the velocity region, as well as the displacement region, right? To get either the 50th percentile or the 84.1 percentile of the response spectrum. So what do you do? Based on our understanding, I'll go a little bit slow here. We have the pseudo velocity plot along the y-axis. We have the natural vibration along the x-axis. or the natural period or along the x-axis, or frequency. In this case, it is shown in terms of frequency scale. We know that for a very low time period kind of a structure, the peak ground acceleration will be the same as the peak structural acceleration that will be observed. For a high time period or a low frequency, for a flexible system, the peak ground displacement will be the same as the peak displacement that is observed from the system. So there is no increment. So this dotted line shows the peak ground acceleration. You remember the accelerogram that I showed in the beginning of the response spectrum ka jab session shuru hua, the part when it started, we saw an accelerogram in representation of the peak ground acceleration of the ground motion, and this represents the peak ground velocity and the peak ground displacement of the ground motion, not of the structure. So Newmark and Hall, what they said, okay, in the initial part, this is the same as the peak ground displacement as well as the peak ground acceleration. I will give you certain factors. Now, P to C is that particular region, if you remember, where the amplification in the acceleration does not depend upon the time period. It depends only on the damping ratio. So that's why they gave this particular amplification with respect to damping ratio. So let's say I have 5% damping that I'm considering for my RCC structure, building or bridges. I take my alpha A and alpha B and alpha D to find out my median value of the response spectrum curve. I multiply my peak ground acceleration with this alpha A. I plot a line. Let's say I use a scale and I plot a long line. I use the same with respect to displacement. I use alpha D into ground displacement. I get a peak line here. And then I plot another line with respect to the scale factor for the velocity with respect to whatever is the peak ground velocity that I'm getting from the ground motion that I've considered. I get that horizontal line. So our line with respect to this till here is created. Our line till here is created. I join this to this, A to B. I join E to F, and that completes my procedure for preparing an elastic design spectrum. Why we are calling it elastic? Remember that this response spectrum analysis we have done using a linear single degree of freedom system, which means we have considered only the linear response of the single degree of freedom system. That is why it is an elastic design spectrum. The one that is given in our code is also an elastic design spectrum, even though we bring it in elasticity by using response reduction factor, etc. That way it comes as a non-linear response spectrum curve we can prepare. But whatever is given in our code with the MC response spectra that we see is a linear response spectrum curve. So what is the procedure for elastic response spectrum curve? Multiply the peak ground acceleration by alpha A to obtain the straight line VC representing the constant value of pseudo acceleration. Multiply peak ground velocity alpha V to obtain the straight line CD representing the constant value of pseudo velocity. Multiplying alpha A, alpha V, and alpha D to the peak ground velocity, peak ground acceleration, and peak ground displacement to get the corresponding um, displacement spectra, pseudo velocity spectra, and the pseudo acceleration spectra values for the response spectrum curve. And then joining the lines with respect to the peak ground acceleration for the low time period and the peak ground displacement for the high time period kind of system. I hope it is clear, right? So, but for Roorkee, let's say once again coming back to Roorkee itself, you might have a site wherein there will be different sources, like sir tomorrow will be covering up, or today might be covering up the deterministic seismic hazard analysis and the probabilistic seismic hazard analysis, wherein we look at what are the different sources around the particular site of concern. Like if I'm building up a new structure or a bridge here in this particular location, I need to look at what are the different seismic sources around the my site of concern, right? There might be a huge source, I mean large a source which can produce a higher magnitude, but it might be very distant. And there might be a very a site which might be very close to the particular region which might produce a low earthquake. So what do you consider the large earthquake with respect to this thing for your design of structures? Yes, that might be the process that you might be doing in terms of a deterministic seismic hazard analysis, where you're looking at a controlling earthquake. But in terms of considering that there is a possibility that even the large earthquake at a large distance can have also have an impact on your structure, what you do is you can plot the response spectrum for that particular uh, uh, case and the other case also, and then the combined, I mean the hatched area that you see considers both the cases. I mean that way you need to consider your response spectrum curve. So if you plot with respect to a set of ground motions, you get I mean, it might be for a near field earthquake. but this particular site has also another fault which is a large distance but can produce a large earthquake. You need to consider that also into the final preparation of your response spectrum curve. That is what I want to intend to transfer this with respect to this, right? So before we move on to our multi-degree of freedom system, just want to recap everything that we have done. Initially, we looked at the equation of motion for a single degree of freedom system, which was a free vibration problem wherein there was no external force which was applied. We applied it an initial displacement and an initial velocity and set it to motion. Right? When we set into motion, what we used that particular solution for, if it is a undammed system to add on, the motion will go on forever. If it is a dammed free vibration, the motion will come to rest. If you find out the solution for the displacement time history, what we normally, the other usage is to find out the natural frequency of the system or the natural time period of the system. And we can also find out the displacement time history of that particular system when it is set into free vibration of motion. Then we looked at single degree of freedom system when it is subjected to external force. Let it be P of t. If I have a P of t, which is like an harmonic motion, sine omega bar t ke case mein some machine is functioning, we know how the classical form of equation of motion is getting solved. We have a homogeneous part, we have a particular solution part, we have to combine them and produce our final solution in terms of, again, we are interested in the displacement time history, and in that also we are interested in the peak value. Again, one thing I said, if there is a transient phase and a steady state phase in terms of a forced vibration, the steady state will remain as long as the machine or the forcing vibration is present, whereas the transient phase is like a free vibration analysis. If it is set into motion, if damping is there, it will die down and only the steady state will remain. If your external forcing function is not P of t, it is a ground motion, then I said it is not easy to use the classical particular plus homogeneous solution to find out the solution to the equation of motion. You need to use some numerical methods also to kind of find out the solution. One application of using the single degree of freedom system, which was used as a response spectrum method, we looked at linear single degree of freedom system. We subjected it to a particular ground motion. We considered varying time periods but a single damping ratio and subjected it to a ground motion, let's say. And we looked at the peak values. We plotted a peak value. We looked at the tripartite graph and we looked at, okay, we already understand how the response spectrum curve is used in our equivalent lateral force method, which comes in our code, which is like the earthquake force, which is calculated as per equivalent lateral force method, is like AH into W. Acceleration seismic coefficient AH multiplied by the seismic weight of the structure that we are considering. In that Z by 2, I by R, SA by G, we use that SA by response spectrum plot to find out our SA by G curve, right? So that way equivalent lateral force method works. In case of response spectrum curve method, we'll come to, in terms of MDF system, we'll come to how that can be further, like modal combinations and all, we'll come to once again. But we looked at the characteristics of the response spectrum curve. For a very low time period, what happens? Very high time period, what happens? What happens to the intermediate regions? There are regions which are dependent only on the damping ratio. There are regions which depend, the amplification varies with respect to time period as well as damping. And Newmark and Hall method, we saw how people have already given how to plot your own response spectrum curve. And the last slide before this particular one was like, single response spectrum curve based on a single ground motion is not enough for the designing a structure. We need to create, we need to use multiple earthquake, which you will understand how to choose an earthquake. When you do DSHA and PSHA analysis, you will get to know what is the governing equation for a site, how much distance I need to cover with respect to how much distance we need to cover around the site in order to understand कौन से fault है which I need to consider. Do I consider 1,000 kilometer away some site is there, sorry, a fault is there, do I consider for my analysis of my structure there or not? That needs to be understood, right? So till now we have covered that particular portion. Now we'll look at this video again. This is again similar to that same shake table. Now we have a multi-degree of freedom system, right? So there is, the mass is same, you can see the height of the structure is the same, the material is same, so means stiffness of each individual story might be the same, the mass is same. It is again subjected to an increasing frequency of shaking of the table. Let's see what happens. Look carefully. and then try to understand what is happening. I'll summarize at the end of the video. So initially the shake table, this is again a uniaxial shake table. Right, you can understand the natural frequency of the system is 4.35. But think, will it have only a single natural frequency or would it have multiple? If multiple, how many? Think of it. See how the upper mass, lower mass, and the middle mass are moving, their relative movement. Kindly see. I'll stop the video here because it's a long video. I'll I'll pause it here and then I'll talk to you. Right. So what you saw is, I mean that video, that image is not coming, but let's see through. Imagine what I'm saying. You saw that on top of that shake table there was three masses kept one on top of other. It is looking like a three-story structure, or a structure wherein the masses are lumped at three levels, right? Better that rather than talking about buildings, it's a structure. It can be a pier also where the masses are lumped at three levels. The moment that it started initiating the vibration at 4 hertz nearly, you saw that the initial frequency, I mean the most fundamental frequency of the system was activated, where you saw that each mass was moving in phase. Like if the lower mass moving was towards the right, the middle mass is also moving towards the right, and the top mass is also moving towards the right. So everything is in phase and things are moving in tandem, like in sync, left to right. Whereas when you saw with respect to the second natural frequency of that particular system, the thing you saw is, yes, the upper mass is moving right, means the middle mass is almost staying same, and the bottommost is moving towards the left. But then whatever that happened at that particular frequency, it was giving the peak response. Like in the case of single degree of freedom system, when we saw the shake table example, the most flexible system, when it's moving rapidly, the other two are quiet. And in this particular system, you have a single tower, which means in the first phase, it is moving towards the right. Every mass is moving towards the right. Whereas in the second case, it was moving little bit in an offbeat fashion. Right, left, right, it might be. I didn't show the third value. There is also third frequency because you have three. I mean, to assess this thing, how many frequencies is going to occur, think back on the degrees of freedom that we talked about. Again, the same thing comes in. Was it a 3D structure? It might be, but the motion was in a 2D fashion. So I'm doing a linear analysis. I mean, a 2D analysis of the structure being subjecting it to left to right kind of motion. So you might say there is an X, there is a displacement U1, U2, and there might be a rotation also coming. The mass was not providing any rotation, leave it out. The column, I might assume it as an axially inextensible, I mean axially rigid kind of a column. If I assume, I need to look at 3 degrees of freedom, that is U1 lateral, U2 in a horizontal fashion, U3 in a horizontal. I mean everything in a horizontal fashion. Those three information that if I get, I can respond to the responses of the structure. So 3 degrees of freedom. If you have a 3 degree of freedom structure, you have three natural frequencies for that system. The first was the most fundamental frequency. The second is the natural frequency. I mean, all three are natural frequencies, but the first one that you saw, the lowest one, that is at 4 hertz, is the most fundamental frequency. I'll tell you why I'm calling it as the most fundamental frequency in the coming slides. So you see all three are going to happen. I showed only two during the video, right? Now again, a free vibration analysis of a multi-degree. We are starting with the same as started with single degree of freedom system. You have a free vibration of the multi-degree of freedom analysis. What I mean by that is, if I have a multi-degree of freedom system and I give you a choice, I don't tell you what is the natural frequency or what is the motion of the structure in which it is going to behave in its natural frequencies. I give you a choice of choosing a particular displacement profile for the masses at the two levels. So let's say the bottom mass you choose, I'm saying in a hypothetical fashion, 10x, and you use minus 1x, which means I'm using 10x, 10 times I'm pulling it this side, this one I'm pushing it to minus 1x, right? If I do some random kind of a displacement profile, or initial displacement, that if I give a certain random values to this guy, the response might not be harmonic. Second thing, the response might not be very high, right? So what I'm trying to say is, if I find out a deformation shape, for this is a 2 degree of freedom system. Again, I'm calling it 2 degree of freedom system by the static condensation thing that I've said just now, and I have only u1 and u2 respond to, to find out. So I'm calling it a 2 degree of freedom system. And if I find out a certain profile corresponding to which, if uh, shift it, like this might be in the ratio 1:2, I might do 2:4, I might do 3:6. The ratio remains the same, but the profile is the same. If I do that, then I get a harmonic response, and that harmonic response might give me the peak response for whatever deformation it is undergoing. Damping is not getting considered, so that is why this is going on infinitely, right? Since it's a 2 degree of freedom, there is another natural frequency, second natural frequency for the system. If you understand with respect to the video that the movement of the masses are not in sync. In the first phase only, in the first natural frequency, it was in phase. In the second one, it was not in phase. So if I do such kind of a deformation, which means I'm pushing this one left side, means I'm pushing a profile in the right side. It may be in a certain proportion. In that proportion, if I give any deformation, 1:2, I keep that proportion same, I again get a harmonic response. So what you understand from this is, if I'm agitating my structure in its natural frequencies, the response will be harmonic. It will be at its peak value. The other thing that you can also see is, if I agitate in certain frequencies, the other frequency is not kind of too much coming into play there. And the third one is, if I subject this particular structure to a particular ground motion, the final response of this structure will be an amalgamation of all these modes, all these kind of vibration that is coming in here, right? You can understand, during an earthquake, whatever that accelerogram showed, it was a varying frequency, varying acceleration. There is no if it's not a sinusoidal forcing function that you have, where you have a fixed natural forcing frequency. It is an earthquake which can have multiple frequencies that is coming into picture. So the final response of a multi-degree of freedom system will be an amalgamation of all these kind of mode shapes that you see here, right? And the final thing that I want to say is, the mode shape is a non-dimensional quantity. It is just a representation of, if I have a natural frequency, it has a particular mode shape that is associated with it. If I vibrate, if the shake table is agitating the table at a particular frequency, let's say for the multi-degree freedom system, 4 hertz was the location where, which was corresponding to the first natural frequency. The system is going to respond in this way itself, harmonic, and it will show the same phase of movement that we saw in the video. I hope it is clear as per my explanation. So you can read, this slides will be shared with you, you can read, this is the same what I've explained till now. And then the way we find out, like, from the shake, we cannot do shake table all along with our multi-degree of freedom system, right? We cannot create a whole it's easy to say, but it's difficult to do that particular problem. So how do you find out, if I have a multi-degree of freedom system, how do you find out the natural frequencies of the system? Do a model analysis. In that, sorry, model analysis is a part and parcel of that process. You do an eigenvalue problem, right? K minus the determinant of K minus m omega square, you must have seen it again and again. If I find out the determinant of K minus m omega square, what the characteristic equation that I get, if I solve it, I get the eigenvalues, right? If I put it back into the equation, I get the eigenvectors, right, which represents the mode shape of the system, right? I'll show an example. I'll come to this slide very soon. Like, understand this particular problem, that eigenvalue problem, if you do that particular solution, you get the eigenvalues and the eigenvectors. Eigenvalues represents the natural frequency of the system, and eigenvector represents the mode shape of the structure or the system that you're looking at. mode shapes are dimensionless. It gives the way in which the masses is going to behave if it is getting agitated at a certain frequency level, right? So TK, I was thinking of showing a problem, example problem, so that you understand it better, but this is also very important. You remember what Weising sir showed with respect to grillage model, and there was a frame or a wire model that was there for a deck modeling, right? So there are three ways in which the deck, let's say, for example, I'm saying the deck of a bridge is getting modeled here. You have two nodes here, but there is no internal number of elements is one in case number one. Free nodes are zero, so there is no node where the mass can be lumped, right? Constrained nodes are two. There are pin supports that are given here, and the total number of nodes are also two. Whereas in the second model, you have two restrained nodes and a free node at the middle of the span. Whereas in the third case, you have two restrained nodes and three free nodes that are available, right? It is dividing. You are discretizing the model into three particular regions wherein the masses will be lumped corresponding to each particular length of the thing. It will be lumped. This is the same deck. Think of it as a deck of, let's say, 30 meters being modeled in different ways. You have free nodes in some models, more in some lesser model. I mean, one model it is non-existent. So what is happening is in case of mode 1, you see that there is no mode shape that you are going to get from this, because there is no free mass getting lumped, and you are not looking at any kind of dynamic response from the system. Where you have a single node at the intermediate location where the masses will be lumped corresponding to the deck that you are considering, you have two translations. You have one like this and one horizontal deformation that you expected from the system. In case of three nodes that you are provided, the three free nodes that you are provided, you are corresponding to that three translations and three rotational displacements, or three vertical displacement, not rotation, because we are not considering any rotational mass there. So you have three translations vertical and three translations in the horizontal direction that you can observe from this. So what is the inference from here? The inference is, if you are doing a structure where dynamic loads are going to get impacted on your structure, right? If that is going to happen, you want to look at the dynamic response of the structure. If you want to look at the dynamic response of the structure should also behave in a dynamic fashion, where all these kind of modes are coming into picture. The mass representation is being given, the mass is getting lumped, and that mass during a particular vibration due to a dynamic load is going to move here and there under that dynamic action. So you want that kind of response. So if you choose very simple model without any nodes, only constraints are given, it is of no use. You can use it for a static analysis. You can find out the reaction in those kind of pin joint, but uh, you cannot do away with such kind of analysis if you want to do the dynamic response of the deck system, right? Consider the sentence that I said. If you want to consider the dynamic response of the deck, you need to consider the different, you need to mesh it properly, you need to discretize it properly, you need to have free nodes where the masses will be lumped, etc. So in case of a pier, this image Weising sir has already shown to you. I can have a model like this, wherein the masses, pier ka mass मैंने lump green color से किया है. The pier cap is being modeled by a lumped mass at the blue color, and whatever comes from the deck, which is a larger blob that you see on top, is being kept here. Or else I can do like this also, right? To consider the live load effect also at a certain height, I'm considering that particular aspect, and the deck is kept on top of a bearing, and it comes, the CG comes at a higher elevation. I can consider that one also. Both are not wrong in their approach in terms of analysis. One is better than the other, you know which one. Think in your mind which one is better. The bottom one is better, which gives a better representation of the distribution of masses in the structure. But this is computationally expensive in a sense that isn't it easy for me to calculate what is the total mass that is coming onto the top of the pier? As sir said, in terms of bridges, the pier is the most important element in terms of inelastic analysis, inelastic response of the structure, because I don't want my failure or inelasticity to get concentrated in the pier, or sorry, pile, like, and it is easy for me to repair if it happens in the pier itself. So deck is simply supported on top of the pier, and the pier is the one that acts as the most important element in a structure when subjected to earthquake, because it helps in energy dissipation by happening those shear and flexural hinges that you happen. Shear, not shear. You don't want shear hinges to form. You want flexural hinges, as flexural hinges is the more ductile response of the pier. So it depends on you on what your purpose is, and then accordingly you need to find out which model is going to work for you, right? So the eigenvalue problem uh, what I said earlier gives you the characteristic equation which you solve to get the eigenvalues and eigenvectors. It gives you a sense of what are the different masses that you have lumped. It's your choice, right? Eigenvalue analysis that the Midas software or any other software does it for you depends upon how you have modeled the structure, what are the free nodes, where and all you have put the masses there, what masses you have put, that and all depends. So let's look at a problem. So this is a 3 degree of freedom system. So you have three masses, three equal masses lumped at three different levels. Accordingly, since it's a multi-degree of freedom system, see, it was not three masses that was kept on top of a shake table in an uncoupled fashion. It was like a three stories, like the masses were one on top of the other, and the stiffness of the columns or the piers at multiple level, not pier, the columns will kind of affect the stiffness of the structures. That's why you don't see a diagonal matrix here. It is a kind of a coupled matrix of stiffness that you see here. So you cannot use here, if it was diagonal, you have three individual equations of motion that you would have had to solve. But since it's coupled, it is not easy to solve. We'll see how to solve it later. But I can do the determinant of k minus m omega square. I can do that and get my characteristic equation. If I solve the characteristic equation, I get my natural frequencies, right? I have varying. So the lowest frequency is 10.45, then 29.28 and 42.31 radians per second. Whereas time period, my corresponding to omega 1, the t1 is 0.6, then it reduces to 0.21, then it reduces to 0.15. So my natural frequency, the fundamental natural frequency in here, even though there are three natural frequencies and corresponding three natural periods that are there equation wise, the fundamental one now we are going to define. Why did I call omega 1 is equal to 10.45 radians per second as the fundamental frequency, or why would I call t1 as 0.6 second as the fundamental time period of the structure? Before that, the eigenvectors are there. You can solve, you can substitute this omega 1, omega 2, omega 3 back in k minus m omega wala equation, and then you can find out the phi 1, phi 2, phi 3, which is the mode shape of the structure, which represents for this multi-degree of freedom system how it is going to behave. Again, mode shapes are dimensionless. It gives you how the mass is going to move if each mode shape, or if it is subjected to that particular frequency, how is it going to move, right? Now here you have two things that are coming in front of you, right? I said dynamic systems, natural frequencies are there, mode shapes are there, mode shape is dimensionless. So if I look at one particular mode corresponding to one particular natural frequency, how much does it contribute to my base shear? How much does it contribute to my total displacement? One mode shape, the final value. See, you are interested in finally getting the displacement time history. I said there is mass, okay, agreed. Stiffness, you agree that is there. Mode shape कुछ देता नहीं है, dimensionless. Then how do I bring them all together? That bringing, stitching them together is done by the participation factor. The participation factor calculated by the seismic weight that you see here. Mode shape is also a variable that comes in here. Ties it down and gives me a factor that 1.22. These are numbers that are coming in. I'll tell you how they come into the final solution. This is a participation factor which gives how each mode shape is contributing to the final answer, right? Keep that in mind. Modal mass is another calculation, a separate calculation that I do. Again, the variables are the same, the seismic weight and mode shape. It gives me how much mass, if there were three degrees of freedoms there, right? If I calculate the total mass, W1 plus W2 plus W3, I get a total W, right? Out of the total W, how much does one, in the first mode, how much mass from that particular W comes into the response that I see from the first mode? So you see 177.19, then 14.98, 2.112 in terms of kg or ton, you can take it appropriately. But what you see here is the mass participation in the first mode is nearly 91.36%. This is why, I mean, out of the three modes, the mode number one, which corresponds to the lowest frequency or the highest time period, contributes the most amount of mass, which means you can simply think in your mind that if I'm looking at a deformation data from the dynamic analysis, this one is, what do you say? This one is contributed mostly by the first mode. The first mode dominates is the word that I was searching for, dominates the response of the structure. If it was 70-20, then you would say, as Weising sir said, we need 90% mass participation to kind of be confident that we have taken up the dynamic analysis, and whatever answer that I'm giving you takes into factor all these kind of dynamic response that the structure will show. So if it is 91.36, I need not even look at mode 2 and mode 3. I can look at only mode 1, find out what is the base shear, what is the displacement, and then go ahead with my design process. If it is less than that, you have to look at it, right? So there is participation factor and the modal mass. So once I've understood my modal mass, what I do with the participation factor is this. So if I need to find out the design lateral force, same as acceleration into mass or mass into acceleration gives the force, the dynamic force or the earthquake force that we want, as in ah into w. What happens is, okay, you have ah, that is the acceleration coefficient, you have w that comes into picture, you have mode shape has to come in, right? Mode shape is what contributes, like kidhar ja raha hai mass wo batane ke liye, but here comes the participation factor. So if I do this particular multiplication q i1 के तौर पे, what I'm getting in different layers is what is the base shear, what is the value of shear based on the first floor, second floor, and third floor. Accordingly, if I use another mode also, let's say 70-20 ka mass participation tha between first mode and second mode, totally it becomes 90. I need to find out with respect to q for first mode, q for second mode, right? And then what do you do once you have found out? I mean, you need to combine the two, right? There you use what is the combination factors, right? I'll come to that. I'll come to this particular side, how it is done. I combine them with SRSS, CQC, or absolute sum, whichever. And you've already understood CQC is a better method in terms of combining the results, right? So coming back to modal analysis. So this is how you find out the forces in the system. One thing that we left out is how do you solve the in terms of if you look at midas in the evening, what will happen? There will be you will be looking at response spectrum analysis. Maybe you will have time history analysis being shown, that what button you need to check to do a time history analysis. You know already response spectrum analysis. Model combination method will come into picture. So what happens in model combination is, rather than solving the equation of motion using time history, I mean directly solving the equation using some time marching scheme, which will come later, what we can do, what is normally done in a multi-degree of freedom system is that, rather than solving for, we are solving the equation of motion is a matrix of mass, stiffness, and damping, we assume. And then the equation of motion is the same, that mu double dot plus u dot plus ku is equal to some external forcing. And whatever response that we get in terms of u of t, right? Rather than solving it in this particular displacement u of t, we are looking at modal coordinate q of t, right? We are representing u of t as modal coordinate multiplied by this particular factor phi, which is the mode shape ka factor हम बोल रहे हैं, particular to one particular mode, right? I'm substituting it in the equation of motion. You look at it here, right? One property that the mode shape possesses is the orthogonality property. You might understand it already with respect to the video that we show. Orthogonality ka property kya hai? So if I multiply with a particular mode phi n of t, where if I consider different mode shapes, what I get from this is a simple diagrammatic representation. Is if I do multiply LHS, all the LHS with respect to, let's say, phi n of t, RHS also with respect to phi n of t, I get this particular, due to orthogonality, what I get is this particular equation as an uncoupled form, right? If you multiply phi 1 is mode shape corresponding to first mode, multiplied by the mass matrix or the stiffness matrix, phi 1 k transpose k phi 1, what you get is a k matrix which is uncoupled, which is only a diagonal matrix. So what does it mean? What does it do is that if I change the coordinates from the u of t to a modal coordinate q of t, use the orthogonality property of the mode shapes, my multi-degree of freedom system then shifts to a single degree of equal and single degree of freedom systems, right? As I said, phi transpose m phi transpose k phi, corresponding to each mode that you are going to consider, will convert the multi-degree of freedom system into individual, equal, and single degree of freedom systems of a certain mass, a certain height, and a certain natural frequency of the system. So what do? You again what you do in this is, since now you have a single degree of freedom system, it is easy for you to solve this particular problem, right? So you individually solve this individual single degree of freedom system, and then you use any model combination method, which means this multi-degree of freedom system, we solve it using eigenvalue analysis. We find out what is the mode shapes, which this may be mode 1, this may be mode 2, right? Corresponding to this particular thing, we convert the multi-degree of freedom system into equivalent single degree of freedom system using the orthogonality, I mean benefiting from the orthogonality property of the mode shapes. And then from each single degree of freedom system, whether it is subjected to any type of load, here time history is there, earthquake ground motion, you find out the responses of the system from there. You find out the response of the same system subjected to that ground motion for that equivalent single degree of freedom system, which you have got from the modal coordinates. Then once you have got the result, once you have got the peak values, the only thing to do is combine them. So again here CQC, SRSS, absolute sum, whichever is the best method that you know, you can apply that. So this is the model combination method that happens when you click this switch in your midas software, which maybe in the evening when you do the analysis in using the software, you will come to understand, right? So this has been taken care of. Now what if I don't want to do such kind of model coordinate transformation? What if I want to do the direct integration or the direct solution for the equation of motion when a time history or a earthquake force externally is applied? So I can use numerical methods for it, right? You can think the fifth chapter of AK Chopra, whatever I have covered today, is exactly the images that I have shown are from AK Chopra book on dynamics. From there you can correspondingly see what the thing is. So the fifth chapter of that particular book corresponds to numerical methods which can be used to solve such type of problem. And there are certain time marching schemes like Newmark method. Why I'm showing Newmark method, there are many others also. You can use Newmark method because midas software mein Newmark method is given there, so that's why I'm showing it here. There are other methods also prevalent here, but what you have to see here is numerical solutions can be explicit as well as implicit. You can see this method is an implicit method, Newmark method, because we are trying to, if the structure is still, which means some u0, initial displacement is 0, initial velocity is 0, and it is subjected to a time history, then what is happening is that we want to predict the value. It's a numerical method, right? It's not the exact solution, it's a numerical solution. So you are predicting what is ui plus 1 or u dot velocity at I plus 1. But while predicting it, you need to find out, you need to have the answer for u double dot of I plus 1 also. So it is like you want to predict, but you need to predict something else in that particular. So this is a kind of implicit solver that you see in terms of the Newmark method. And then you have certain factors, gamma and beta, that comes into picture here. And choosing a certain gamma and beta relates to a certain solution. I mean, you can have constant average acceleration method if you use I mean, you're assuming an average, constant average acceleration, or you can have a linearly increasing, linearly varying kind of acceleration values based on the selection of gamma, the values of gamma and beta. This is already provided in that particular method of how to use it, when to use it. I mean, you can choose any one of them and kind of find a solution. Convergence would be an issue. To get that convergence, you have to choose the correct parameters of gamma and beta and select the time step also, the increment of time step. So Wilson and Bath gives you recommendation that, okay, find out the lowest time period of your system divided by pi, use that as the increment of time period. But yes, you can have varying time period and see. I mean, for a quick solution, if you choose a very small time period, it will take a long time for you to get your solution. So this is the Newmark beta method that is given there in the code. You have to select the delta t, the coefficient of integration is given along with it. The increment in stiffness, I mean, if there is any alteration in the stiffness matrix, which normally doesn't happen if you are doing a linear analysis, then this doesn't change. And then you follow this process. I mean, this is a step-by-step procedure for finding out what is the response. So this is a method that is given there. This is a method that is chosen in certain softwares with respect to the analysis. And once the time history analysis is done, again, I mean, for a particular conversion, like Weising sir said, the time history analysis is the one which wherein all the modes are inherently being considered while we are doing the analysis. So it gives you a final product in terms of what is the peak displacement, peak acceleration. Where you do into model coordinates, where individual modes are separated out. Model combination method means we have separated out the responses of the MDF into individual single degree of equal and single degree of freedom system based on the model coordinates. There you have to combine them at a later, and that is what combines as a modal combination method. The response spectrum method is a separate method wherein that also comes in. Like when we do that analysis, we saw again how CQC comes in. Like if you find out SA by G ke liye, you take your response spectrum curve and then you do the analysis. You get individual mode ke liye Q1, Q2, Q for first mode, Q2 for second mode, you get it. You combine them again using any modal combination method, CQC, SRSS. So that is the whole deal of doing. So the selection of the model becomes the most important issue. Do you want to do a 2D analysis? Do you want a 3D analysis? Grillage model करना है या frame model करना है? That is what I'm saying. If your structure uh, needs that kind of analysis, you need to do it particularly, right? Then the method of analysis. If you have time, if you want to go in detail or depth in terms of doing a time history analysis, uh, I mean, that is the best method that is available. But once you see DSHA analysis, PSHA analysis, maybe selection of ground motion might be also be there as a problem for you. So ground motion selection ka karna bhi is a very difficult aspect that is there. Once you do it, you will understand ki okay, nahi, I mean, it's better I can choose this method or that method, whichever is appropriate, use it, and then you will get an idea of which is, I mean, how far is it? Like once you do a problem, you might be asking me which time history karu ya wo karu. Once you take up a problem, do that problem, understand what are the results that you are getting. If the structure is simple, both methods might give you the same answer. If it bit of complicated, let's say curved bridge, wherein a grillage model might be a better than a single frame model, you will easily understand which one is better. So when I said a curved bridge, you yourself might have thought, "Arey, isme to frame model might be very approximate for the deck analysis. Grillage might be the better one." But I say no, grillage se bhi upar you can do a finite element modeling through meshing, etc. That might be a better analysis to get the final answer. But do you have enough time to go to FE analysis? That is where the question comes and hangs up with the grillage model. That is enough in terms of when you're doing a certain project, etc. Right? So I hope you have had a fruitful kind of 1.5 hours with respect to this. Aman, any questions?
Yes, sir, we have a few questions. We'll take them one by one.
Okay.
Can you suggest something on the MDOF modeling of bridge deck and pier? How many degrees of freedom are to be taken for MDOF analysis of bridge?
I think that is what I said at the very end of this discussion, that um, line model doesn't work much. I mean, it is better either you go for a grillage model or you go for an FE kind of a continuum model kind of a thing. But continuum model will be very cumbersome and very this thing. Most accurate will be the FE model, but still grillage model is fair enough. It
Sir,
depends. It depends upon the problem also.
okay, Mr. Pulkit is asking, are there any standards slash codes that guide how to carry the shake table test, how to scale the models, etc.? Which one is largely accepted in India?
Uh, there is a book on, I mean, those are two questions. Shake table ke liye, see, one thing is there, it's as easy as you have a strong machine that can shake the table, first of all, without any kind of frictional force coming into picture. You can place an accelerometer on top of the table to see whether whatever ground motion that you want to give is getting put into the system as it is. There should not be, the table on which you put should have a strong kind of a base. I mean, it should not deform while you're doing this analysis, right? Scaling के लिए I don't personally know any code for doing shake table test, but there is a book which can be used for scaling the model. If I say it correctly, it's Subnis, SABNIS. एक author का नाम only what I remember right now. It is a book wherein if you are modeling, I mean, if you are testing a structure, obviously on a shake table you cannot bring the whole big structure. I mean, yes, there are e-defense I mean, that laboratory in Japan wherein you can full scale testing can be done. But when you're scaling structures, like whether it is a pseudostatic test or a dynamic test, scaling ke liye sabse best book is by the author Subnis, wherein the similitude relationship ke bare mein they have explained it in detail. I would tell you to refer that book, precisely that book.
Okay, sir. Mr. Krishna is asking, what design measures can we use to mitigate the resonance impact in bridges?
See, it depends ki earthquake mein to resonance hona, it's very rare. It cannot happen because the frequencies are very much not in tandem. You have multiple frequencies coming in, and that is why resonance is a very rare, I mean, rare or extremely nil kind of a thing that happens during an earthquake. If you are talking in terms of let's say vehicle movement ki wajah se or pedestrian ki wajah se, there is a good example, Millennium Bridge in like London, where it was a pedestrian bridge. When it opened, it started vibrating. I mean, resonance, it's like, it's not like as soon as resonance happens, like if I shake the table, we saw in terms of single degree of freedom system at 4 hertz, the system started to vibrate rapidly, right? But suddenly when you shifted away from that frequency, it stopped. So even if you solve that equation of motion for a resonance kind of condition, it is like the resonant response grows on you. It is like not suddenly the deformation increases, it increases very slowly, matlab it does it, but it happens in a gradual manner, it increases in a lot. So what you need to do is, if your loading is going to create such a kind of action, you can provide additional damping devices, you can provide additional stiffening. That is what they did in that particular bridge. You can I'm sure that it is a Millennium Bridge. It is like they kept a name for it. You can just Google it and kind of say shaky bridge or wobbly bridge करके डालेंगे तो you will find out how they mitigated it by providing viscous dampers at the bottom, providing additional stiffness in the system. It is easy to mitigate. I mean, it's first of all, yes, if resonance comes in bridges, it should not, because earthquake cannot produce such kind of resonance in totality. If it comes due to any moving loads or anything, the only thing you can do is to, I mean, it will not be a kind of permanent thing, right? You can yourself understand by even with moving loads, it is just a transient phase of the loading that happens. So in that phase, when the deformation is increasing, it will not increase indefinitely because it is not permanent on the bridge. In that moment, when you have maybe microsecond or a 1 second region where the resonance does happen, you need additional measures like additional stiffness and damping to be provided.
So Mr. Pulkit is asking, in any FM software, there are two types of participation factors. One is displacement based and other is mass based. What is the difference between these two?
No, that has to be checked. I mean, in the evening, I would request Mohit and all to kind of check in terms of key, when you do this particular analysis, what is it asking karke? What I have said with respect to is with respect to the participation of the modal mass in terms of the analysis. That is what Q1 into 5 into uske basis पे मैंने दिखाया था. But I need to be sure with respect to what is being done in the software.
Why is it, Mr. Bharat is asking, why is it essential to apply base shear corrections when conducting a more detailed analysis to ensure accurate results?
Is that reference with respect to the correction factor of VB bar by VB that he's asking?
I think so. I think so.
That is because see, when you do normally, if you do equivalent static force method, you understand that most of the dynamic analysis method, whether it is response spectrum or time history analysis, if you check the base shear that you get from that particular static analysis versus dynamic analysis, the dynamic gives you a lower value, right? But the code says ki, okay, with respect to your analysis, it's better that once you consider the structure, whatever you have modeled might not be stiff enough, or you might, like if I model a building, I might not be modeling the masonry into picture. So there are certain assumptions that you're doing in your model analysis, or your model analysis in the sense your numerical model that you're creating in your software. So in order to have that, okay, static, my measure is this much, demand is this much, my dynamic method is coming low, my modeling might have affected that particular kind of lower value. So in order to have a balance, like, so it says, okay, do some correction factor VB bar by VB, such that I can uh, increase it at that at minimum level. I need that much amount of force for which it needs to be designed. That is the case. So dynamic analysis remains the same, dynamic mode consideration remains the same, only the forces that you consider will be amplified. That is all that is being done. So it's not altering any dynamic thing that is coming into the analysis, dynamic expression.
Now this will take a couple of questions more because we are running out of time.
Okay.
Mr.
Maybe you can
yes, sir.
Maybe you can copy all those questions and maybe
Yes, sir. We can take them later.
Yeah.
Okay. Maybe last one then.
Yeah.
Okay. Mr. Dharmendra is asking, how do I select ground motion for a particular city, and what are the type of faults that can be considered, and
I
what
think that is being
level we should
covered.
consider?
that is being covered under DSHA and PSHA analysis, right? Kumar? Yeah, so
Right.
you should hear it from Vising sir's mouth itself, because no one is better than him in explaining that. So I request you to wait for that particular session. Don't miss that session, because that is the most important session in terms of one part is assessment of the demand, one part is modeling of your structure, and one part is reading the analysis. So all three are important, and that session will help you understand how to choose your ground motions for a particular location, as I said. Right. So
Okay,
listen it
sir.
to that particular session.
Thank you very much, sir, for your very informative session. It completes more or less 2 semesters of masters here. So,
Thank you, man. Pleasure
so
was all
we'll
mine.
take a break of 1 hour maybe, and we'll come back at 2. I will also exit the session here.
So, thank you.
Thank you.